Metamorphism tells us about plate tectonics, orogenesis, and the thermal structure of the continental crust. It's a key part in piecing together how modern and ancient plate tectonics operates on Earth. And the record of metamorphism can be interrogated one way through archives such as those Mike Brown's been using over the years. In this talk, I'll focus on one extreme manifestation of metamorphism, that of ultra-high temperature metamorphism, or UHT. So UHT metamorphism was recognised around 4 decades ago, but was not widely accepted until the mid to late 90s. At this time, Simon Harley started quantifying the thermobarometric conditions of various UHT assemblages. When Dave Kelsey put together a review in 2008, he had just under 50 occurrences, and when he updated that with Martin Hand in 2016, they had just under 60 occurrences. So what is UHT metamorphism? Well, it's considered an extension of granulite facies metamorphism, temperature cutoff above 900 degrees, and a pressure cutoff around 750 degrees per GPa. And the idea is that this coincides with the kyanite-sillimanite boundary. So I produced an updated database of UHT occurrences using existing datasets combined with recent papers. We now have around 80 UHT occurrences. Here these are plotted on their present-day coordinates, colour-coded for age, and on the right with the age versus geothermal gradient plot with the Brown and Johnson 29 database in the background. So one of my primary interests in looking into the temporal and spatial patterns of UHT was to establish when and where they formed in true continent-continent collisional orogens, and when they formed in accretion orogens where you have ongoing subduction. So I categorised the 80 locations into these two types, and I've lumped interplate orogens with the collisional types. Of course, this sort of exercise is like opening a large can of worms because many of the UHT terranes have highly debated origins with a wide variety of opinions on their tectonic settings. So exact results are not fixed, but are what I consider a best estimate. So here are the results of my analysis, plotted below on the age versus geothermal gradient plot. We have accretionary types in blue, continent-continent collisional types in red. Now, several older UHT terranes don't fit into these categories very well. The people who have worked on them have probably sensibly steered clear of defining tectonic settings. And there's on here 4 definitive examples of contact metamorphism. And this top part of the figure shows kernel density estimates, with the same data, so the height of the peaks reflects the abundance of data. We can glean the first few order patterns from this analysis. Firstly, both collisional and accretionary types occur throughout Earth's preserved record of UHT metamorphism. Secondly, during periods when we form the supercontinents, which we see by these vertical bars, we see an increase in UHT occurrences, and we also have both collisional and accretionary types forming during each supercontinent cycle. And lastly, during breakup periods of supercontinents, we see rare to no UHT metamorphism, which correlates with the lack of orogenesis globally. Now, in the literature, there are numerous mentions of the correlation between supercontinents and UHT metamorphism, but few papers mention what causal links there might be. The primary question of any geological record like this is the pattern in the preserved record due to patterns in generation or patterns in preservation. The fact that the complete metamorphic record is also biased towards supercontinent formation periods tells us that perhaps there's no special link between UHT and supercontinents. Now, digging deeper into this temporal and spatial study, the location of these UHT terranes can further inform us about any potential links. Here I've plotted in the present day positions the location of the 80 UHT terranes during the 4 periods broadly associated with supercontinent formation. Based on these, I've crudely located the UHT occurrences upon reconstructions of the supercontinents. Here's Columbia on the left at 740 MA, Rodinia on the right at 1050 MA. Both of these have UHT metamorphism forming with the internal orogens that were created as these cratons collided together, as well as UHT metamorphism occurring on the margins of the supercontinent in accretionary belts. Now, Gondwana and Pangaea have fewer preserved UHT terranes. For Gondwana, all of those actually occur internal to the supercontinent, but they do comprise UHT metamorphism in accretionary settings, and Pangaea has very few occurrences. The take-home message of the spatial summary is that UHT conditions are found both within the orogens internal to supercontinents and with those forming along their margins. So the key question is, will these subduction margins know that they are part of a supercontinent? And if not, and I would argue not, I think we can potentially throw out a UHT supercontinent link in terms of a causal process and stick to the question of preservation bias. Now, another way of looking at where UHT metamorphism occurs is analysing which geodynamic environments can we get to UHT conditions. We can achieve this through interpretation of the geological record, but also use thermal models and geodynamic models. Now, I don't have the time to delve into all these in detail. I'm going to summarise the results on one of the seminal thermal model studies. This was done by Chris Clark and colleagues, published about 10 years ago now. This is a crustal thickening model, and they showed a combination of processes helped to get to UHT conditions, namely burial of rocks of high radiogenic heat production, low erosion rates, because these keep hot crust at depth, and suppression of melting, because melting buffers crustal temperatures. They showed that thickened back arcs do not reach UHT conditions, and the orogenic plateau best fit these criteria. Now, the orogenic plateau model has been invoked for various UHT terranes, especially those that are large and long-lived, such as those in Gondwana across Madagascar and South India. In terms of suppression of melting, it's also been invoked that preconditioning of crust by previous orogenic activity helps reach UHT conditions in later orogenesis. In terms of the geological record of these 80 occurrences, various mechanisms for providing the additional heat flow necessary have been invoked, as have various tectonic settings, including arcs, back arcs, arc-continent collisions, continent-continent collisions, and intraplate orogens. I don't have the time to summarise all of those. I want to pick up on one key observation. So Chris Clark said in his paper that UHT metamorphism is typically not associated with the intrusion of substantial mafic or ultramafic rock, ruling out mantle-derived magma as a major heat source. Now, the literature, particularly in the last decade or so since that statement, does contradict that somewhat, because both mantle heating and magmatism are both processes invoked in quite a large number of UHT settings now, around a third. So although orogenic plateau may be one of the most viable settings, particularly for bigger orogens, I think what this tells us is that there is more than one way to skin a cat. So how can geodynamic modelling help? Well, geodynamic models can tell us what temperatures are reached within the crust and what paths are taken in PT space. So I've simplified the results of various models for collisions and arcs into a set of cartoons, and the main feature I want to draw your attention to is this dashed white line, which is a 900-degree isotherm. Now, in most continent-continent collisions, we've known for quite a long time that temperatures don't get that high. You're going to need a lot of radiogenic heating over a protracted period of time. If you want to increase the temperature on a shorter timescales, those relevant to smaller orogens, you need a mechanism for lithospheric thinning, which brings the hotter mantle close to the crust. Two potential ways of doing this are through slab breakoff, as has been recently proposed for the Gruff complex in the Alps, although in this case, slab breakoff probably actually occurs much deeper than drawn here, and this is based on the model of Jeff Ullman et al. Just recently. And another mechanism is slab rollback. This can potentially open up a channel for hot mantle to rise and get closer to the lower, over-thickened crust. And this is perhaps a viable mechanism to explain how we've got to UHT conditions in the Himalayan orogeny in the Miocene, as evidenced by a recent paper by Wang et al. And what about continental arcs, we see here on the left? Well, stable arcs do not reach elevated temperatures, but there's at least a couple of ways of perturbing the isotherms. One is through arc extension. The other is when we have compressional arcs and we get an uprise of hot sediment melt diapirs. But both of these are probably very transient heating events, probably unlikely to produce UHT conditions on any kind of grand scale, but they might produce some of the shorter-lived UHT that we see. Back arcs, on the other hand, that we see on the right, are a popular setting for UHT metamorphism. This has largely been due to the paradigm of Roy Hyndman and his colleagues, demonstrated that modern back arcs are very wide regions with hot, thin, or hot crust, hot high fluid flow, and thin lithosphere. They link that to small-scale convection in the mantle and thinning of the back arc lithosphere. We know that opening the back arcs can get the lower crust quite hot, and when you close these, you can bury this hot crust. So in the Phanerozoic, it's probably hard to get to UHT conditions in arcs and collisions, orogens, without radiogenic heating and magmatism, which is known as preconditioning the crust. What about deeper in time? Well, you've probably all seen plots like this. They are estimates of mantle temperature through time. We know firstly that the mantle was hotter in the past and probably peaked around the Mesoarchean. And two, the mantle temperature at any one time probably has a significant amount of variation. Now, mantle temperature has implications for orogenesis through its effect on things like strength of the lithosphere, density contrast between the lithosphere and the asthenosphere, and of course the abundance of melt. So to summarise the results of various geodynamic modelling studies, what we see with increases in mantle temperature can be summarised to a few points. We see common retreat of the convergent plate. It generally always has shallow break-off of this lower plate. There's abundant decompression melting in the asthenosphere, much more than we see at present day. And one way of exposing the crust to hot mantle is by peeling back the continental lithosphere. Now, depending on the initial conditions provided in geodynamic models, collisional orogens can be cold, with stacking of crustal blocks, which are more similar to modern orogens, or can they be hot or ultra hot, with abundant crustal magmatism. But regardless of the geometry of these convergent settings, we see two common features: lithospheric thinning over wide areas and mantle heating of the lower crust. Both factors are likely to facilitate UHT conditions being reached. So to summarise, we see UHT conditions in the modern environment, indicating that supercontinent amalgamation is not required, and nor are the hot mantle temperatures of the past. Modelling shows that UHT conditions probably more easily be attainable in the past because the crust and the mantle do behave differently. So shouldn't UHT metamorphism be more prevalent in deep time? Well, clearly the record preserved today is highly biased by preservation and not what is produced. Perhaps that's not surprising, given the likely retrogression and overprinting of UHT rocks that's going to occur in younger orogens. So finally, what do UHT rocks tell us about the overall coevolution mantle and continental tectonics through time? I would argue the UHT record shows us that at least the ability to generate and preserve low pressure and high temperature conditions has persisted for 3GA. Here we can see a rather constant maximum temperature of metamorphism through time. Which leaves two ongoing questions, because it's the record of preserved high pressure and low temperature metamorphism is actually more inconsistent in the record. Key question is, when does the ability to produce and also preserve these gradients occur in time? And that's something we're going to hear more about during this conference. So to summarise, the known UHT occurrences are increasing in number, and we have several examples now in recent history and in various tectonic settings. There's no direct link of UHT metamorphism to supercontinents, although I have not had time to explore was the mantle temperature hotter at this time. And their record is dictated by preservation. It should be more prevalent in the past. UHT metamorphism can form in a wide variety of settings, preconditioned and orogenic heat, perhaps the reasons that many orogens are only localized UHT because these will be variable. And links between duration and setting I've not discussed, but the lithospheric mantle thinning is perhaps the most unifying feature overall. And I thank you for listening.
Okay, thank you, Nick. So I've got a comment in the chat from Simon Harley. So certainly you've shown that there's lots of different ways you can form UHT terranes. So do you think that a way forward in differentiating between them is to think about lots of other factors like the scale, the timing of the magnetism, the nature of the magnetism? When you're a geochronologist, do you think one way to differentiate between these different tectonic settings would be through integrating other techniques? It does seem like there's more than one way to form them.
Yeah, I mean, I got into this through my studies in Norway, where we're linking magnetism much more with the metamorphism. And I guess that is the angle I've been coming from the most, is the role of magnetism is perhaps maybe not being underappreciated, but just not being quantified. And that definitely involving that in models is probably the next step, because the older models often don't have things like magnetism involved, but the more complex geodynamic models do. And just reading the rest of Simon Harley's comment.
That's fine. Yeah, then one other question, Nick, was how do you reconcile your inference of thin lithosphere with the seismologically derived estimates of thick lithosphere under present-day mantle belts and under the geological remnants of ancient belts? So I guess the zeniths from the Tibetan Plateau do show UHT conditions at depth.
That's a good question. I like Wright Hyman's model, but I'm looking for the geodynamicists to tell me which bits are right and which bits are wrong in that model, because I've tried to find geodynamic models with small scale convection drawn like they do, and I can't find any. So I think there's a lot of work for the geodynamicists to do to help people like me who are putting together just kind of broader implications. Just reading the question. Yeah, I don't have a good answer for that, Alex.
Great. Okay. Well, thanks very much, Nick.